Welcome, welcome to the pre-recording of lecture 42 of computational geometry. So this is a lecture that comes at the very end of this course. Actually, it is the next to last lecture where we are going to review for the final exam scheduled for 7 May. So in this lecture, I will present 6 sample questions to kind of focus on some of the most important um, problems that we have considered, mainly for the first half of the course, with the addition of a question on three-dimensional convex hulls. So the exam is happening in the afternoon, in the middle of next week. The final exam covers everything what we have seen in this course. So we have the topics on the first midterm exam. So this review will focus on these 5 chapters in the textbook. In the next review, we will look at the topics for the second midterm exam. And today we will also do something about the three-dimensional convex hulls on that problem. The other problems that will also then be considered in the next review. So this review is aimed to prepare for the final exam. There is in no way that we can offer a complete coverage. The exercises are actually a much better way for doing this. And also, of course, there is the first midterm exam and the second midterm exam. So the exam will be open book. And you will need a computer, but you will need to upload your answers into Gradescope. So the exam is kind of a hybrid between an offline, off-campus electronic version exam and an in-class version. Okay, I have prepared 6 questions, and every question is kind of introducing or reintroducing one slide. So when I was thinking about a question, I was thinking about what is the background, what are the concepts that we consider. So in the beginning of the course, we talked about constructing convex hulls, and we saw that this actually corresponds to ordering the points that span the convex hull, ordering them in such a way such that two consecutive points they span an edge. You can actually look at the convex hull then as a sequence of vectors. And here these vectors are ordered clockwise. So in the example, you see the input, 5 red dots, and it represents essentially a triangle. So the convex hull is a triangle, and the points, the vertex points in this triangle are connected by the edges, which are oriented. So you can see this as a sorting problem. Okay, what happens if you remove a vertex? So we have on input given Q. Q is a list of n clockwise ordered points. So they represent the convex hull. So on the example of the previous slide, this would be a triangle. And then we have a point that is not in the convex hull. So how do you extend the convex hull with this point? In some sense, this is inserting in a sorted list. You must locate where you have to insert, and then you have to insert. It's a little bit more complicated than that, as we will see. So, but the question is, how would you do this? And also, in some sense, it is more complicated than inserting into a list of numbers, because after all, these are points. But in some sense, it's not the same hardness again as with sorting, as with constructing the convex hull itself. So we will actually see that you can do this in linear time, linear in the number of points, the size of um, your input list queue. Okay, um, if we think about the convex hull, we see we are given a list of ordered points, but actually what we see are these arrows, we see these vectors, and they are ordered clockwise. So we these edges, they actually also represent lines that cut the plane in two. And the point that is inside the convex hull is actually always at the right side of the edge. So if the point is at the right side of the edge, then actually that edge is good. Okay, so, and that's also one way to decide whether a point is inside the convex hull or not. You actually look at the angle that the vector defined by the edge spans, and then also the angle with the start point of the edge and ending at a point. So if that angle is right enough, is less than pi, then actually you know that the point is at the good side, belongs to the convex hull. Okay, but we are given a point that we know that it doesn't lie inside the convex hull, so there is at least one edge for which that point is on the wrong side. So the point is on to the left. So we call that edge actually the first edge that concerns us, because all the previous edges, well, they can stay. Okay, so we have then a new edge, the edge that connects the point to the start of the edge with the new point. So that's a new edge. And then we have to decide what we do with this point B. So does it stay or does it go? So you can think of a picture where there is we have this kind of a pyramid with the top of the pyramid is the new point P, and the base is actually was that edge AB that goes, but we now replace that edge AB by A, the top of the pyramid, and then P to B. However, it could be that the next point lies actually not at the right side of PB. It could be that the edge PB actually points inside the convex hull, and if you would connect B to C, you would actually have not a convex hull anymore. So if that happens, you have to remove B from the list. And then you have the edge that is the new point to that next point following B. And you may have to continue with this. So you can think of the point P that lies very high up and that causes the removal of many next points. But at some point, you will actually end up again at an edge where the point P lies at the right side. So there is a loop that is done here. So it may correspond that the insert is just an insert as in a list. You just insert the point between A and B, but it may be that you have to remove many points B and some of the following points. Okay, so this is the algorithm in sufficient detail. This is described in words. When I was thinking about this algorithm, I had pictures in mind. You can always scribble on, you can always make drawings on a sheet of paper to explain the statements. Okay, how much does this cost now? Well, we have endpoints, and if you have a planar convex hull, then you also have n edges. So the algorithm of inserting a point is actually edge oriented. So we have to traverse. In the worst case, it could be that uh, the last edge has to be replaced, and that is actually the edge between the last point and the first point, because we reason cyclically. Now, and that's kind of the worst case. Could be that it also can be done in constant time, but in the worst case, we have n steps, as we have to consider all points in that list Q. All the operations that we are doing involve an angle computation to decide whether the point lies to the right or to the left of an edge. So, and they can be done in constant time. So adding one extra point to a planar convex hull can be done in linear time. Okay, that's our first review question. The second review question concerns line segment intersection and the overlay of maps. So here is one slide which I've taken of one of the previous lectures to motivate, kind of to explain the background to the question. So what do we have? We are overlaying uh, we are overlaying this triangle with this map, which could, so we had the square inside the pentagon, and then we imposed the triangle on this. So the map consists of line segments, and the points at the intersection of the edges of the pentagon with the triangle and the square, the inside square with the triangle, these are the new points, that the new intersection points that were computed with the overlay of this map. Okay, so what we introduced is then the graph that represents the cycles. So for every phase, and the faces are identified in this example here by the yellow dots. So we have 7 faces. So every face is represented by, it's identified by this yellow vertex, but it is represented by 2 cycles. So we can run around the face in the outside. So in the outside, we do this in a clockwise fashion. So that's the outside cycle. And in the inside cycle, we are running around in a counterclockwise manner. So, and we identified, so the words on the slide, so the first sentence uh, defines the outside boundary to each face, and then we have the inside boundary of each face. So we have the first face, the outside boundary to this first face is actually the entire plane, not so interesting. But then we have the inside face, the inside boundary inside to that first face that has the outside, which shares edges with the outside of the faces 2 and 3. So a lemma that we then used to update the data structure to represent the overlay is actually saying that if we have this graph, then with every connected component, we have the set of cycles that are incident to one face. Okay, so that's the background for the question. So if you now look at this lemma, so we can look at the proof of the lemma as well in the textbook. But actually, what the purpose of the question here is that how would you represent those faces? So this is in some sense computational geometry as a second data structure course. What is the application of the doubly connected edge list to represent the statement of that lemma? So how can you represent the cycles, so the statement, the set of cycles incident to one face? How is that stored in a computer, in a data structure? Okay, I can go back to the previous slide, but I actually recycled that picture. So in some sense, the answer to this question is actually with a picture, with an example. So we have the first map that was the pentagon with the inside face, the square, that was intersected by that triangle. And I focused on one of the largest connected components, and I indicated the connections. So we have the cycles in the graph. So the nodes in the graph are the cycles. The connections correspond to the edges. In particular, we have the face with marked 6, and that shares an edge, a red edge. So the red edge lies at the outside cycle of phase 6. So it's part of the outside boundary. And it also is in the inside boundary of phase 3. So go clockwise around the outside of phase 6 and go to the twin of that red edge, and you will go in the inside of the phase 3. So one can look at the green edge that lies on the border of phase 3 and phase 5. So that green edge lies at the outside of phase 5. So you go clockwise from 7 to 5. If you move on the outside cycle of C5, but in the inside cycle you take the twin, you take the opposite direction. Okay, so then we have now we have 6 components, 5 components. So we are actually now I'm sorry, we do have 6 components, but we have 5 edges. So the orange edge starts at the vertex 7, which is used to identify the face 7. So the orange edge, if you traverse it clockwise, you are at the outside boundary of phase 7, but you are at the inside if you go in from, say, from that vertex 7 downwards, then you are traversing the inner cycle of phase 3. And then we have the brown edge, which is on the boundary between phase 3 and phase 4, and the same reasoning can be made. So this is how the inside is connected to the outside. And there is also the second face that has the black edge on the boundary with phase 4. So all the cycles incident to one phase. So here we are actually looking at phase 3, which contains 3 edges that are on the outside of phases 4, 5, and 7. And we have the the face 3 shares an outside edge with the face 6. So this is how one should interpret this set of cycles and how they are connected. Um, More in particular, how is this represented by a doubly connected edge list? And here, actually, I should have, if you are a little bit more freer with drawing, and I don't know if I actually should attempt do this. So we have the, probably I shouldn't, perhaps I should, will try. So here I have this edge. If I go clockwise, I'm actually at the outside. So I go here. So, or if I go inside, then I go counterclockwise. But actually, in the slide focuses on the red edge. In the red edge, I go outside. Um, Outside, I do this clockwise. So I go in this direction. Inside, I go in the opposite direction. So actually the red edge is represented by twin edges. And the orient, so from an edge I can go to the twin, which also means that from one face I can go to the adjacent face. So the purpose of this exercise was to show the purpose of the data structure, the doubly connected edge list, to represent a subdivision. So ultimately, when one is overlaying two maps given by doubly connected edge lists, one is computing a new doubly connected edge list. And this graph played one important role in constructing this overlay map. Okay, partitioning a polygon. We When we triangulate a polygon, if the polygon is convex, then it can be done in a very straightforward manner. You just pick one vertex and you add diagonals to the opposite vertices. Now, if the polygon is not convex, then you can make it Y monotone. Y monotone is not yet convex, but it can be triangulated efficiently. So here the lemma is important that it kind of characterizes what it means to be Y monotone. It's formulated in kind of a negative way. If there are no split and no merge vertices, then the polygon is Y monotone. And in the proof, we see two pictures. So the first picture shows a line and it's cutting the polygon. And if you look at the intersection of the line with the polygon, it's a horizontal line. So the line is actually represented by a height, y. And that intersection consists of two disjoint line segments. So if you can draw a horizontal line through a polygon and you get disjoint segments, then that means that the polygon is not Y monotone. So this is a very special case for not convex. So you can see that the examples are not convex. And you see the two cases, either you have a split vertex or you have a merge vertex. Where it comes the terminology from? Well, so you work up or down. So if you move the line down and the polygon becomes connected, that is the case in the left, then you have a split vertex. In the opposite way, if you are moving it up and the polygon becomes connected, then you have a merge vertex. So these are the two type of vertices. So this proof is very interesting in many reasons because it is essentially reformulating the definition. And if we had forgotten the definition of a split and a merge vertex, here it is. And it also shows the relationship between the property of a polygon not Y monotone, that then there must be either a split vertex or a merge vertex, as is the proof by contradiction showing. Now, once you have identified the split and the merge vertices, you can then partition the polygon by taking the split vertex or the merged vertex and connecting it with another vertex. So the importance of the split and merge vertices, that was important in the partitioning of this polygon. Question, how many split vertices can you have? The question actually starts here. In this review, I'm trying to start with the concept and then formulate the question. I could have done it differently, so where I start, this is the question, and then you have to start thinking, where did we cover split and merge vertices? Now, we actually now know where we encountered them. So in some sense, half of that question is already solved. Now think about this. Uh, how many of those n vertices can be split or merge vertices? And how can you demonstrate that this is a bound, and is this a sharp bound? Okay, the answer is a picture. You kind of consider a comb-shaped polygon. It's kind of a strange comb, but I was working from the pictures from the proof. So here I have 4 split vertices. You can see that if the line intersects this convex hull, we have many line segments, 1, 2, 3, 4, 5. I count 5. So these are also the number of peaks, and then I have one bottom vertex. So I was trying to get as many split vertices possible, and you can kind of see that if you have a split vertex, you must have 2 vertices. Otherwise, you can't really have 2 disjoint line segments. But the peaks, they can be shared. So in some sense, it's not really that you have twice as many, or actually, if you have here an even number of vertices, so we have 10 vertices, we see that we have 4 split vertices. And of course, this reasoning also happened if you flip the picture, then with one top vertex and then many bottom vertices, then you can make the similar reasoning for the merge vertices. So here I focused on the split vertices. So the answer is that you can have about half as many split vertices as the total number of vertices. So this says also something when you partition a polygon that is not Y monotone, how many pieces can you get? So that's actually the motivation why you might be interested in the answer to this question. Okay, 3 of the 6 questions answered, so I'm 30 minutes in. The next topic, that was chapter 4 in our textbook, concerned linear programming in 2 dimensions. And for that, we considered the intersection of convex polygons. So convex polygons arise naturally, when you consider the linear inequalities, every linear inequality represents a half plane. The intersection of half planes defines a convex polygon. In some sense, this is the alternative way of defining convex polygons, either as the convex hull of finitely many points or as the intersection of finitely many half planes. So if we use a divide and conquer way to solve a linear program, we are intersecting the feasible regions. So in the language of linear programming problem, the convex polygon or polyhedron, if it's not bounded, the that polyhedron that contains all the points that satisfy the inequalities, that polyhedron is called the feasible region. If we apply a divide and conquer method to solving linear programs, so first considering the first half and then the second half, computing the optimal vertex and then intersecting, then we need to intersect polygons. And again, these polygons, as in the first question, they are given by ordered set of vertices. So here we have red region and a green region, and we are intersecting them. So the blue, and there are two different cases that are being considered here. So it depends where the blue is, the blue lines, the blue edges define the intersection of these two polygons. So in the first case, we have the green polygon that cuts out into the red region. In the other case, to the other side, we have the opposite. We have the red polygon that cuts into the green polygon. Okay, how do we find these blue edges? So the blue edges are actually new, but they're also defined by the points that are the vertices that are either vertices of the red and the green polygon, and we have new vertices, the intersection points. So in some sense, we're going to intersect edges. So that's the background, intersecting of two convex polygons. Assume that these two convex polygons are given by two ordered lists. What is then the cost of computing their intersection? So we are going to compute a new ordered list of points by considering the convex hull of the first polygon and the convex hull of the second. Now, if you consider this as the line intersection problem, this could become quadratic. And it could involve also a sorting. But remember that the lists are actually ordered clockwise. So if we go from one point to the next, they are connected by an edge. So just saying we're doing all possible combinations and see which ones of our new intersection points are vertices or not is not a good algorithm. We can do this a lot smarter. Okay, what is the cost? Well, if you think about the cost, what is actually the right way of computing this? Well, the algorithm that we have covered in class, so the slide was actually taken from the reasoning of this algorithm, we apply the sweep line algorithm. So what I didn't talk about on this picture was the sweep line. So we compute the left boundary and then the right boundary starting at the topmost point. So in both convex polygons, we go to the top, the point that is highest, and then we are starting to merge these boundaries. So every vertex is called an event point, and these points, they are candidate vertices. So depending on which side of the edge that they are lying, but we also have to compute intersection points. Now again, the intersection points, if you do this in kind of intersecting all possible edges, which is a very bad and dumb thing to do, because you only intersect at adjacent edges. So you actually know when there could be a new vertex or not. So we are actually not sorting, so this is not an n or n plus m logarithm of the total number of points. No, we can actually walk. We walk actually twice, once to the left, once to the right. And we are going to visit all the points of both polygons. And the operations that we are doing in each step are constant, deciding on which side that we are, computing a new event point. So we have an algorithm that runs in linear time, linear in the size of the input. Okay, so this was, by the way, a lemma that we have proven. All right, range queries, another data structure. And we talked about split vertices. Here we have split nodes. So we have a sequence of numbers, and we want to report all the numbers inside a query range. So here we have numbers ranging from 3 to 105, and we want to report all the numbers in the region 20 to 60. So the numbers are stored in a balanced binary search tree, and a split node is the first node in that tree that lies inside the query interval. So that means that we may have to search why is the split node called a split node? Well, if you look at this example here, 62 is outside the query range. So that means that we can discard everything to the right of 62. So this corresponds to a binary search, which goes very quick. So in some sense, we very quickly identify a split node by either choosing the left or the right, as long as we are not yet have encountered the split node. Okay, so now comes the question. So these range queries, they are output sensitive. So if we do a binary search, then we know that this happens in logarithmic time, logarithmic in the number of leaves of our tree. Now, if we have a rather large range, then we may need to report many points. So it could be not logarithmic in the size, but it could be linear. In the worst case, we have to report everything. Okay, now the question is, can you actually predict this by the depth of the split node? Now, by depth, I'm referring, so the tree that I've shown on the previous slide was like a biological tree. The root is at the bottom and the leaves are on the top. But most trees in computer science are actually more like the roots of a tree. The root is actually on top, and then we have nodes that are deeper and deeper. So that's also what I mean by the depth of the tree. So the size of the input, so you're going to very quickly find that split node. and you can record how many levels down that you are, assuming that you know the entire depth of the tree. So can you predict something about the output size? You can think why this would be useful. Well, it could be useful if you have to allocate memory, or if you have to warn somehow the user, hey, there's going to be a ton of data, a ton of numbers scrolling on your screen. So you can prepare something. So that's the purpose of this question here. Okay, so in trying to decide the answer, we observed already if the split node is the root, then actually the root lies in the query range, and then you may have to look to the left and to the right, but you may have to report everything. So that's the upper bound, everything. It could also be that the split node is just a leaf. And then actually you have to report only one number. So these are the two extremes. Now we can reason from the leaf. We have only one point, and each time it's a binary tree. Each time when we go one level up, or the depth decreases by one, I mean, here I normalize it that the depth is 0. If we say that depth 0 is at the leaf, and at the root we are at the height of the tree, then in each case the size of the output can double. So actually the size of the output is 2 to the power d. And the argument is phrased in the last sentence. Okay, um, last question on three-dimensional convex hulls. So my timing is kind of good. So three-dimensional convex hulls was kind of the last chapter, chapter 11, that we covered well. So I plan to have at least one question on after the second midterm. So three-dimensional convex hulls are a good candidate. We considered incremental algorithms. So we have already the convex hull in of a finite number of points, and we consider one extra point. So here is a representation. I hope the perspective is fine. So we have a facet. The top facet is this triangle, this blue triangle, and we have the green plane that is represented by the outer normal vector, the vector that is pointing outwards. So you should imagine that we stand on this face and we look up and we can see the point. So we can see that new point, and because we can see it, that means that we will have to remove the face we are standing on when we consider the new convex hull. So the incremental algorithm that we considered was by looking at which points are visible from the existing facets and identifying then the new facets that are going to be spanned by the edges of the visible facets and the edges that are connecting those visible facets with the new point. So that's kind of the picture that you have to keep in mind at the following question. So we are reasoning backwards. Instead of adding, so we're going to, it's very similar to where we started with planar convex hulls. We're going to update a convex hull, but instead of adding, we're going to remove a vertex. So our convex hulls are represented by doubly connected edge lists. So we have the edges that are running around our facets. And we also have, so we have edge lists, so we have vertex tables and then face tables. Now the point is, consider the removal of one vertex and the update of the convex hull. So essentially the update of this data structure. Now for simplicity, we are assuming that all the facets, they are all triangles. So if not, then you triangulate the facets. How would you explain how this removal process works? And also, what is the cost of this update? So how many operations would you need in function of the size of your convex hull Q? So we have n vertices, we're removing one of them. How much do we need to remove? But first, let us try to think about how we would go about defining an algorithm to do this. Well, when I explained the picture, I had to hold back a little bit and not say the word. The word is actually the horizon. So what this picture showed were the picture with the facets from which you can see the new point. That is actually the horizon. So if you remove a vertex, what you're going to have is that you have all the facets that contain that vertex as on its boundary. So they are actually all triangles. So what is remaining of these facets are the edges. So we actually have a sequence of edges, and that will actually determine the horizon. So this is actually what is left. So you can think of, um, so in no matter which vertex you pick, you can always rotate your polygon so that that vertex is actually the top, the very top of your convex hull. So it's kind of, you have a house and you remove one of the corners of the roof, and also then all the uh, sides that contain that corner. So what you remain are the edges, and then you have to connect those edges with facets. So you need to add all the facets on the horizon. Um, so the key answer was here the horizon, and in defining that horizon, you see that the edges of that horizon, they can actually come in very um, naturally. So in defining the facets on the horizon, again, you may assume that these facets will be triangles for simplicity. We just pick always random points. Then you're going to have adjacent edges on the horizon that you connect with a new edge. Um, so what is the cost? Well, it could be that you have a polytope that has one large base, that's a flat polygon, and you are removing just the top of this pyramid, and then actually you have to run over all the n-1 remaining vertices. So in some sense, the cost is at least linear. Now it's bad, but not that's actually a worst case almost. But it's not that bad because you still have the connectivity of your horizon. So actually, your horizon already lists all the edges in order. So you have actually the consecutive edges that are connected to each other. So it's not an n log n operation anymore. You don't need to sort. So because the doubly connected edge list still contains the connectivity of the edges on the horizon. So the other important point is we have to compute new facets. And again, the new facets of a polygon with n vertices can be linear. So it can be that if you have to construct a whole new roof, that indeed you have to visit all remaining n-1 vertices, but not more. So the sorting has been done here. So the removal of one vertex can take you as much time as the remaining number of vertices, but not more. Okay, I'm done 50 minutes in, so my timing was fine, and I hope that this first review, gave somehow a good overview of many of the important concepts in our computational geometry class.